Welcome all. We'll study EM waves today, and it's a short topic, so we would be able to cover it a little quickly, and we would have some time for some of the remaining topics which we have. And like I was not able to complete polarization in the last class, so I'll be completing that today. See, before I start EM waves, EM waves is one of those topics. There are topics, if I consider this as the syllabus, there are some topics which are, this is the JEE mains, this is the JEE advanced, and this is total is JEE mains. This is in the form of sets, sets, right? There are some topics which lie in this zone, which are not a part of the JEE advanced syllabus, but are a part of JEE mains, right? So these topics in physics, they include this EM waves, okay? Classical magnetism, Earth's magnetism and magnetic materials. Classical magnetism. Okay. In this, from wave optics, diffraction and polarization. Then optical instruments also. Okay, no question of this came actually, but it's very hazy. This topic is hazy. It may come, it may not come, because it is ray optics itself, direct. Semiconductors and communication. Right. In the first year, when JEE was, this curriculum changed. JEE was transformed into a single exam to 2 exams. Thank you. Just a second. In the first year, when JEE was transformed from single exam to 2-stage exam, 12 questions out of 30 came from these topics. In 11th, there is one topic also. This was free forced and resonant oscillations. Free forced and resonant and damped as well. I forgot damped actually. Okay, this is in 11th, this is all in 12th. Okay, rest all topics of 11th are a curriculum of JEE advanced, are in syllabus of JEE advanced as well. This topic of 11th is not a part of JEE advanced syllabus. Okay, all these topics, from all these topics in the first year of JEE means 12 questions out of 30 came, which is a huge number actually. You can understand that these topics, they form only around 20% or maybe less, 15% of total 11th, 12th syllabus, right? But out of them, around 40% paper. Even though these days it's not the same actually. These days it doesn't happen that 12 questions will come out of these topics, but 6-7 topics still come from these topics. And the important thing with these topics is they are easy. They are hell easy, and people ignore them. Most of the traditional coaching institutes, they ignore them because they had not been a part of JEE curriculum earlier. So difficult questions have not been framed in these chapters, and so they make a very boring kind of class actually. Okay, that's why traditionally they are not taught. They are taught here. You definitely know this. So please, it's very important that you study all these topics, even more as compared to the other traditional topics, okay? Because the possibility of getting a question from these topics is really high. Even in last year, around 7 questions came from these topics, right? So every year this happens. The cutoff is 33%. So in physics, you need to score to crack only 10 questions correctly. I said no negative marking. Okay, you mark 10 correct questions, and out of these 10, 7 are from this chapter. How about that? How about that? So they make a very important, contribution into mains. And we would be discussing EM waves today. We have already discussed this. This diffraction I have discussed, polarization I would be discussing, it's easier. And optical instruments we have discussed. These two also we would discuss. As I earlier said, you can, for semiconductors, communication, I don't remember it was taught last year or not. I don't remember exactly. But semiconductors I taught last year, so you can search for that lecture. It was taught in January end. Okay. So CBSE UDAAN class 12th in YouTube, you can search in that channel. Try to pick those topics, those classes which were taught at end. I'll try to dig out the link. Okay, so if possible, I'll give it to you. Okay, to online people, it will be available in the next class only, because after the class, I'll be able to search. Okay, so offline people can have the link from me right away. Okay, so you can pick that topic from there. Okay, if you want the feel of a live class, obviously I'm here. But if you want to have something prior to the original class, prior to the live class, it would be a great help. Okay, so let's start with EM waves. Can I erase this? These are the important topics, as I said, which are important for means, not for advanced, and that's why ignored. See, electromagnetic wave. Before I start, I would be discussing something else. Electromagnetic waves, in our curriculum, it's not discussed in that detail, right? हम लोग बहुत ज़्यादा नहीं पढ़ते हैं EM waves. Only two derivations are there. One is of displacement current, and the other one is of energy density. Yeah, that's it. Okay, there is a derivation how to find the speed of wave, but that's beyond our curriculum. Okay, it's not that difficult, वैसे, but it won't fetch any marks, so we shouldn't be spending any time on that. But it is a very important topic as far as physics is concerned, as far as engineering is concerned. Okay, its important role, the role of this chapter comes in when we have communication systems. When we build communication systems, you will study in communication chapter. In fact, you must have studied that a lot of communication is wireless. Okay, it is it is very good or bad, I may say. Like, I'll tell the good side and the bad side, that we are able to detect only the visible region of the electromagnetic spectrum. See, the bad thing is that we are unable to detect all other radiations, so our sight is very limited. Okay, some animals, they detect other radiations as well. Okay, UV and infrared, they can detect that much, but we don't. Frankly, it's a boon actually. See, the thing is, right now, the amount of communication systems we have everywhere, mobile phones, TV remotes, everything, the radiation from sun, everything is EM wave. So right now, this room is actually kind of flooded with these EM waves. If we can detect all possible EM waves, just imagine, it would be very mind-boggling for us. It would be a lot more than we can actually understand, right? So it's very good actually. I say it's very good that we understand only the visible region, right? Okay, but these tiny phones, or earlier there were pagers, from these to huge aircraft, everything depends on EM waves, right? So importance is all told. Now, I won't be discussing the first topic of EM wave. First, I would be discussing LR circuits. Okay. You do remember that we discussed RC circuits. Okay, RC circuits were, when a capacitor is charged with a resistance in series, and when a capacitor is discharged. LR circuit would be similar to that. Okay, why am I discussing? The result would be identical as well. Why am I discussing it? because in this scenario current varies in a similar fashion as it did in the RC circuits. If you do remember, in an RC circuit, this was the arrangement and connection was made here, right? Connection was made like this. So as the capacitor was charging, the charge on the capacitor was given by this C E naught, where E is the EMF of the cell, C is the capacitance. This is the resistance. I accidentally attached 1 minus e raised to power minus t by CR. This was it. Do you remember? We used to call it the time constant, right? So we used to write it as Q naught 1 minus e minus t by tau. The current was was a derivative of this, so it was E by R e raised to power minus t by RC, or it was actually I naught e raised to power minus t by tau, right? You would find exactly similar things here, right? Okay, you would find exactly similar kind of expressions here even in LR circuit. So let's start. This is connected at t equal to 0. E is the EMF, L inductance, and R is the resistance. You know, as current grows, as current increases, what happens? The inductor produces an induced EMF. Okay, I current goes in this direction and inductor produces induced EMF in opposite sense, so as to oppose the change in current, right? So if you write here, this would be positive, this would be negative. The voltage across this would be L di by dt, right? Voltage across this would be IR, okay? And E is the EMF. So if you remember Kirchhoff law, so in a loop, if we start from here, you would get plus E from here to here, then minus L di by dt minus IR is equal to 0. This is by KVL, right? Kirchhoff voltage law. And you can write L di by dt is actually E minus IR. Okay, so di by E minus IR is equal to, in fact you can take before this step, take R common, divide both sides by R. Why am I doing it? You will understand. Okay. Okay. Here I did what? Dividing by R. Okay. If I divide it by R, this thing happens. So now di by E upon R minus I. You can take this as I naught. Okay, E by R as I naught. So this would be simpler to write. I naught minus I is equal to R by L dt. Integrating it, initially the current was 0, finally it is I, initially the time was 0, finally it is t. Right? So you know this is, what kind of form this is? Huh? dx by a minus x, यही है ना? dx by a minus x. This would take the form of ln log natural, right? So ln I, in fact there would be a minus sign because the coefficient is negative, minus I naught minus I, and the limits is 0 to I, R by L into T. So shifting this from this to other side, you get ln I minus I naught, I naught minus I, sorry, minus ln I naught is equal to minus R by L into T. And shifting ln there, it becomes E RHS. So 1 minus I upon I naught, or keep it this way only, is E raised to minus R upon L T. So you can sense that this is taking the same kind of shape as our other expression was taking. I naught E raised to minus R, I am writing it in this kind of format. Okay, I'm taking R as denominator of L, right? Okay, and if I write I would be I naught 1 minus E raised to minus T by L upon R, where L upon R is tau, the time constant, and I naught is E upon R. Okay, so this takes same kind of shape as the other one, as the RC circuit, and you can understand this is growth of current actually, section A. This is section A, growth of current. Okay, there would be another thing called decay of current, in which the expression would be I naught E raised to minus T by tau, है ना, on similar lines as the RC circuit. You please write this, I'll write the decay as well. Can I start with the second part? Don't worry, I would not be actually deriving the other thing. I'll just show you the scenario. Now B portion is decay of current See, this is what is happening. You know, for long time, a steady current was flowing. Thus, connections 1, 2, and 3. What is happening? 1 and 2 were connected for long time. Okay. Okay. So what would happen? The current would become how much? You can understand after long time. From this expression, can you understand this? After a long time, this second thing would become 0, right? When t becomes infinite, this becomes e raised to minus infinite, or 1 by e raised to infinite, which is 0, right? So current would be I naught, which is e by r. So steady current of value e by r was flowing actually. Okay, due to long time connection. Now what we do, we connect 2 and 3 suddenly, and now what happens in this scenario? You already know When current was growing, inductor would have stored half Li square energy. So what happens? The inductor tries to maintain the current through it. So initially it will try to maintain I naught current through this circuit. I have made a wrong connection actually. It should be something like this. From here to here. Connection is made like this. Now these two are connected. Actually I accidentally connected E with a wire, which would result in battery shorting. Okay. So now inductor would try to maintain I naught current through it. But as its energy decreases, you already know that the current would also drop. Is it okay? So you obviously can write, I'll write the equation. This portion is not in our concern now. The current, since current is flowing like this and inductor will support the current, are you really okay with this? Inductor will support the current. So it will try to apply EMF in the same direction as the current. The resistance would do what it does best, obstructing the flow, right? So the voltage across this inductor would be how much? LdI by dt. So if we start from this point, plus LdI by dt, then minus IR is equal to 0. Rest there is nothing else. Okay? And you can find I from this. This would be I naught e raised to r minus t by tau. Right? Tau is still the same, L by R. Okay? As I said, I won't be integrating all this second time. So for growth of current, the graph is this. Okay, asymptotic curve. This is I naught. For decay, this is for growth. This is for decay. This kind of thing happens. Okay. So at tau time, current grows to 63% of maximum value. At tau time, current drops to 37% of I naught time. So this 63 and 37, these are the important points which decide actually what kind of circuit you are having. A circuit which has low resistance will allow rapid increase in current, and one which has high resistance will allow slow increase in current, right? So that kind of scenario. So it's the graph actually which is important to us. Okay. The derivation is not that much important. It's just the graph and the expression, right? So we would be discussing this since we have finished this. And we would be taking up this as well in this chapter. Okay. I'll erase the right portion. I have already done it. Okay, so let's start now. I hope this is all done. Every one of you has done this. Let's start with EM waves now. You already know EM waves are what? Electric field and magnetic fields coupled together, right? Electric field and magnetic field coupled together. Actually, in this chapter you will learn that whenever there is a changing magnetic field, a changing electric field will be produced definitely, and vice versa. So they cannot exist standalone. Only constant magnetic field and constant electric field can exist standalone. Okay. If they are changing, other one would always be present. In this chapter you would learn. So let's start how people discovered actually EM waves. Let's start. is the topic running, and now this is the first topic is displacement current, right? Okay. So what is displacement current? We'll study this now. You remember Biot-Savart law, right? Not Biot-Savart law, sorry, the Ampere circuit law. Yeah, you remember the Ampere circuit law? Actually, mix up. Okay. It said, you already remember this. It said that whenever there is a current carrying wire, you can have an Amperian loop. Okay. And if I is the current, then it said that B dot dl for this loop would be mu naught I. You know, we solved it, we found B to be mu naught I upon 2 pi r. Okay, pi का confusion तो नहीं है ना? L dl integral dl would be 2 pi r, right? So now this law is actually true only when currents are steady. Okay, we would prove this law wrong in our situation. Okay, and that's from where a concept of EM waves generated, right? Now imagine this is a circular capacitor plate, another circular capacitor plate. Let's say they are connected through a resistor, okay, to a battery. Okay, now what happens? Let's say at t equal to 0, a connection is made. So you can understand the current would grow and positive charge would increase on this plate and negative charge would increase on this plate. See, I would draw a simplified version of what actually was did, then I'll draw the actual diagram. Okay. So this is a simplified diagram. Okay. What simplified analysis I would present, and then we would see the actual analysis. Slightly different, but it becomes easier once you understand this. So you know what Ampere circuit law said. Let's say we have, I have another marker, so I'll pick this to differentiate between the Amperian loop. I hope this is clear, right? This is the Amperian loop. Another Amperian loop here in between the plates. This is 1 and this is 2. Okay. So for loop 1, Ampere circuit law said what? That B dot dl closed loop integral would give me mu naught I. Obviously this is correct, and you can find from this that B would be mu naught I upon 2 pi r, where r is the distance, r is the radius of the Amperian loop or the distance of point on which you wanted to calculate the field, right? Now for loop 2, since no current is flowing through this loop, this is 0. So for loop 2, you can understand B dot dl would be mu naught I, which is 0. So from this we conclude B is 0. Okay. Ideally this should have been the scenario that in this region, there are magnetic field circles like this. Okay. While in this region no field exists. Here everywhere there are magnetic field circles. Magnetic field is in the form of circles, right? Okay. While in this region no magnetic field exists. This is what the law said, right? But actually when this region was inspected, a magnetic needle was placed in between the capacitors. Okay, it deflected, which showed that actually the magnetic field V is not 0 here. There must exist some magnetic field lines, even though the deflection was smaller compared to this region. Why? Okay, understand it? Okay, I'll explain why in the later portion. So you understand this, that with so many circles it becomes a little confusing. So please understand, the black one are the capacitor plates, right? Red are the magnetic field lines and blue are the Amperian loops. When the capacitor is fully charged. When capacitor is fully charged, no more current flows. When capacitor is fully charged, it gathers same voltage, okay, same potential difference, E, okay. Since it has same potential difference, no current flows, okay. So magnetic field is 0, even around the wire and even inside. So again the loop fits well. Again the law basically fits well whenever there is constant current scenario, okay. Even magnetic field is 0 in the gap, even around the wire it is 0. But whenever there is this scenario when current is changing, is increasing or decreasing, you can understand that whenever current is decreasing, same kind of scenario would happen. Okay. Now let's understand, actually Maxwell said that actually Ampere forgot to consider a term in this scenario. Let's discuss that term. Can I erase this? So what Maxwell said, that actually as charge increases, let's say initially there were only two electric field lines. Now as charge increases, more and more number of electric field lines would increase. Okay, the charge on capacitor, by Gauss law, you understand the magnetic flux, the electric flux is nothing but charge upon epsilon naught. Okay, so charge on any plate can be written as upon epsilon naught. Charge on any plate can be written as this thing, phi e. Okay, okay. So for wire, we used to say that current would be dq by dt. Just pay attention to this. For wire, we used to say current is dq by dt. Now if I differentiate this thing, I get epsilon naught d phi e by dt, which means that whenever flux through a surface is changing. Now imagine our old Amperian loop. This is our old Amperian loop. Okay. As the capacitor is charging, the flux through the Amperian loop is increasing, and whenever there is an increase in flux, it should result in some current. From this logic, we can see. Okay, so he said that actually what happened, Ampere forgot this kind of scenario in which there would be a current because of increase or decrease in flux, change in flux, right? So change in flux causes current, which is not actually a flow of electrons, it is a flow of electric field. More and more electric field lines would start from here and end at this point. Okay, to represent this, he introduced this term. Now this current is called displacement current. Okay, so displacement current is nothing but epsilon naught d phi e by dt, which we can write as E dot A by dt, right? So he said that actually in a circuit, two types of current can exist. Two types of current, they can be conduction current, the normal current through a wire, and a displacement current. Okay, so what happens, these two, they do not exist simultaneously. If conduction current is existing in the wires, then displacement current would not be existing in the wires. If displacement current is existing in between the space, then conduction current would not be existing in between the space. Okay, only one of them exists. Okay, and that's why for continuous wires we always got the right result, right? because displacement current in those scenarios was always 0. Okay, so he modified the Ampere law and said that actually this should be equal to mu naught. I is the total current, so it becomes IC plus ID, which is mu naught IC plus ID would be epsilon naught d phi E by dt. Okay, so he added this term and he renamed it Maxwell Ampere Maxwell circuital law. Okay, he named his he added his name as well. Okay, so the thing is, Maxwell was a very brilliant scientist of his time, and most of his equations involve a lot of differential equations. Okay, at that time he was very adept with solving differential equations. So even in this form also he introduced some sort of differential thing, right? So you understand that displacement current is just another current. Whenever induction current cannot exist, displacement current may be exist in scenario, and the total current becomes sum of these. So let's have a few questions on this. Can I erase this? In fact, let's have a discussion before this. The actual diagram which Maxwell made was this. Because this is